morning students. I hope all of you have completed the dipole concepts. So I hope you have solved already some problems based on that dipole concepts. Now today I am starting this important concept and important theorem for this total electrostatics. So now that is nothing but Gauss law and electric flux. First we discuss about electric flux, what is electric flux, and then we discuss about the Gauss law. The Gauss law is an important law for this electrostatics theory. So first let us see this electric flux. So generally that flux in the sense we use that flux for the fluid flow also, fluid flux. It is nothing but some flow. Something is flowing or something is continuously changing, then we call that as flux. So now here this electric flux is nothing but similar to that of fluid flux. Fluid flux in the sense that if you are considering some fluid is flowing through a pipe, for example here. So now here I am taking this area of cross section of this pipe is suppose say A, or then we can write this flux as that flux is nothing but we write here it as rate of flow of this liquid. That means now this is the volume, the rate of flow of this liquid. So which we can express it as like V into A in this case. If suppose that area of cross section is where V is the velocity in that region. If suppose this area of cross section is making some angle theta like this. Suppose this area of cross section we are taking an element area like this. Now this is the direction of this velocity. So we write this as dV by dt is equal to, I can write this as AV cos theta we can write here. We are taking component of this field in the direction, perpendicular to the direction of this velocity. That means the component in the direction of this velocity or the projection of this area in this direction, normal to this velocity we need to consider. So that means we can write the value as AV cos theta we can write. Now this is nothing but we can name it as fluid flux, the rate of flow of this fluid per unit time. So that we call that as a fluid flux passing through this given area. Now such a similar quantity we define in here in electrostatics here. So electrostatics is nothing but the means there we define some electric fields, electric field lines already. So we can generalize that electric field lines and we define this electric flux here. So this electric flux we can define it as, similarly now suppose if I consider a small area in the field region here. Suppose if this is a small area we are taking here, that means I am taking a small area here where this area we can represent like this. Now the electric field in this region is suppose along this direction here. So there such that there is an angle theta here. Now the flux passing through this small elemental area we can write as, now this is a surface, on some surface, this curved surface we are taking a small element of area dA, and so now in that region I am taking this electric field is along this direction here, and so now the electric flux passing through that small elemental area we can write it as, so that we represent with our d phi. So d phi is equal to E into dA cos theta we can write, or we can express this as d phi is equal to E bar dot dA bar. So that is the flux passing through that small elemental area. And so now here the dA bar means it is an area vector. So that means now we consider that area as a vector quantity, right? And we discussed already in the vectors like a vector product of the vectors, properties of the vector or the product of the vectors if we consider, in that one point is there. Like if you are taking the P bar and Q bar as two adjacent sides of a polygon, or suppose two adjacent sides of this parallelogram, then we can write this P bar cross Q bar will represent the area of this polygon here, right? And so now that area, the magnitude of that area is given by modulus of P bar cross Q bar. And so there we know cross product of two vectors will give us a vector quantity. That means there itself the area is a vector quantity there. And so that means here also now from here the importance of this area vector is there here. So here in Gauss law we consider that area as a vector quantity whose direction is always normal to the surface at that point, right? If it is a closed surface, we consider it as an outward normal. The direction of area is taken as outward normal. If it is just as a open surface, just if a plane if you consider, then its area is taken as just normal to the surface. Depending on your requirement, you can take the direction of that area here. So that here I am taking this area vector, right? Now this E bar dot dA bar is nothing but that use of flux passing through that. So what actually this flux will represents? So we are defining mathematically like this. And if you want to calculate the total flux, we need to integrate this expression here. Therefore, this total flux I can write as, so phi is equal to integral of E bar dot dA bar we need to write. This is the total flux expression simply. Now here what actually this flux will represents? What is actual general meaning of this flux means? This flux will represent the number of electric field lines passing through the given area normal to it. If you are taking a particular area here, so suppose if you are taking a particular area here, how many lines of force are passing through the given area normal to the surface? So that number actually that is representing this electric flux here. That is the general representation of this electric flux. So electric flux is nothing but number of electric field lines passing through the given area normal to it, normal to that surface. And so that flux, that number only we consider as electric flux here. Mathematically it is defined like this. Phi is equal to integral of E bar dot dA bar. And so now we can write this value as so A into dA into cos theta. Suppose if the field is uniform field, if I write, right? If the field is uniform, therefore this phi value we can write as E into E cos theta. Cos theta will also remain same. We are taking a plane surface for example. Then dA we can write here. So which we can write it as E into A into cos theta we can write. Means if theta is also same I am considering here. That means angle between field and area also remains same throughout the duration. So in that case that theta also we can write outside this integration. So then we can write this finally as EA cos theta. That means when a plane surface is placed in a uniform electric field for example, then if you want to calculate flux passing through that, then simply we can write this as EA cos theta. Right? So just find the definition. Electric flux. Electric flux represents the number of electric field lines, passing through the given area and a normal to it. Passing through the given area and normal to it. The electric flux passing through a small element can be defined as the product of electric field and a component of area perpendicular to the field. That is d phi is equal to E into, now this dA cos theta is nothing but the area perpendicular to the field. Because we are defining the lines of force passing normal to that area only we count here. So I am taking the projection of that area. Anything will be both are same only. So then that means E is equal to dA cos theta. So we can express this as in dot product. So phi is equal to E bar dot dA bar. So total flux we can write as is the flux passing through a small area. So the total flux we can write as E is equal to integral of dA cos theta. That means means integral of E over dA per unit, right? So that is nothing but again we are writing the dot product E into dA into cos theta. If the field is uniform and the surface is also plane surface, that means theta is also constant, and E cos theta we are writing outside. Then integral of A, then you can write this as A cos theta, right? Now from the definitions, from these equations itself, we can calculate some points regarding the flux. Like if I ask whether it is a vector or scalar quantity, flux is either vector or scalar, we can observe these definitions here, right? We are expressing the flux as dot product of two quantities, dot product of field and area. The dot product of two vectors gives a scalar quantity. So therefore flux is a scalar. So mention some points here. Flux is a scalar. Next, what is the unit of this flux? So the unit of this flux is nothing but, you can write by using these different units we can write here. So by using these definitions we can write this as, this unit of this field is nothing but, I can write this as Newton per coulomb into meter square, right? Or that can also be written as volt per meter into meter square, which is nothing but volt meter, right? And you can also write this as Newton into meter, you can write it as joule. So joule meter per coulomb also you can write. And so then all these are called this is Newton meter square per coulomb. That means 1 Newton meter square per coulomb. That is equal to 1 volt per meter, 1 volt into meter, and that is equal to, we call it as Weber, which is represented with the WB. So this Weber is the SI unit of this flux here. Sorry, that is magnetic flux. Sorry, that is for magnetic flux it is a Weber. So we can write here it as a unit of this flux as voltmeter. Or this is Newton meter square per coulomb. So that is a electric flux. So in magnetism also we define such a flux here, but we call magnetic flux. So this is, we are calling it as electric flux. So that is a unit of this flux now. And so now here next we can mention some quantities here. That means when the flux will become, that means flux can be positive, negative or zero. Mention that also. Flux passing through the given area. Flux passing through the given area can be positive or negative or can be zero. Next point. Generally we take some sign convention. Automatically if you are taking the proper theta value, you will get the sign conventions there. That means write that the flux entering the surface, the flux entering the given surface is taken as negative, and the flux leaving the surface is taken as positive. Flux leaving the surface is taken as positive. Let us see this example here. This is a cube for example, then I am taking this as A, B, C, D, E, F, G, H. Suppose say now this cube here. This is another axis that is considered here. Suppose say X, Y, and Z axis. Now suppose it is placed in a uniform electric field here. The uniform electric field will be along this x-axis. So E bar is parallel to the x-axis. So it is totally lying in uniform electric field here. It is parallel to this x-axis. That uniform electric field is parallel to x-axis. Now we need to calculate flux through the different phases here. So let us see how to calculate the flux through the different phases. Now we can use this formula. Phi is equal to A cos theta because field is uniform and that surface or plane surfaces we are taking, right? And so now for this flux I am writing this. So our formula is phi is equal to EA cos theta. And here mention some that area about the area vector also. So mention that as another point here. Here we take that we consider area as a vector. Here we consider area as a vector. So before that, let us write about the area after continuation of these some points regarding this. Here we consider area as a vector whose direction is always normal to the surface at the given point. Always normal to the surface at the given point. If the surface is closed, the area vector is taken as outward normal always. That means for any plane surface we consider as normal to the surface only. If it is a closed surface, we should take it as outward only. We should not consider that as a inward direction here. And so now here, now keeping on that about the area for the area throughout this, we need to remember that point here. So whenever you are taking it as a closed surface, it should be along the outward normal only. For example, if you are taking a sphere, so it should be along the radially outward direction there. That is the area of this spherical at any point. If you are taking a small element at any point, the area direction should be like that. So not only for this, but any closed surface. Now here we are taking the cube. Now let us take how to take this area direction here. Now the area of this cube, for example, face ABGH. For this, if I consider, then this area vector will be along this direction. We can write the area of that face. Now that area of that face is opposite to the circular field lines here, right? And so the angle between them is 180 degrees. So that is why we mentioned one point here. The field entering the surface is taken as negative. So here automatically for taking the sign convention, it will get this negative sign here, right? So now let us calculate the flux through the each surface now. Flux through the each surface. Now I am writing this flux through the ABGH. So that surface I am writing here. E is uniform field we mentioned. Uniform means magnitude will remain constant throughout. Direction also. And E into, suppose let us take this as a sphere of side L I am taking here. A cube of side L I am taking here. So it is L square into cos 180, right? And so this is flux ABGH is equal to minus E into L square. That is flux through the ABGH, right? Now I am writing the flux through the opposite face. Opposite face means this one. Now flux through CDEF. Now for this, E bar is like this and our area vector is also like this one. A2 bar, outward normal. So the plane is like this, then our area vector will be like this. And field is also in the same direction. So this will be E into L square into cos 0 you will get. So then E L square you will get. So this is flux through that face. Now let us come to the flux through the remaining phases. For example, now I am taking the flux through this ADEH. This space if I consider. Then for this place, the area vector will be along this direction. That means parallel to the z axis you will get. But field is along x direction. So that means they are perpendicular to each other. And so then the angle will be 90 degrees. And so then angle is 90 degrees means that flux will be same. And And similarly for its opposite face if I consider, then same thing you will get. And next if I consider the top face. Now for the top face the area vector will be along this direction here. And this field is along this direction. So they are perpendicular to each other. So flux of passing through that will be 0. And similarly for the bottom face if I consider, this is A4 I am taking here, then area vector will be like this. And so then that also 0. And for this place also, for this side is also 0 and back side also 0. That means BCFG. For this plane also the area will be along the z direction you get, and field is along x direction you get. That means now the for the remaining all remaining 4 surfaces or 4 faces, then electric field and area vectors are perpendicular to each other. And so you can conclude that the field due to the flux passing through those faces will be 0. That means now I will write here for remaining faces, those are, so A3 we are taking here, so let us write like this: EF, GH, that is one face, and the opposite face is ABCD, comma ADEH, and this back side face will be BC, FG. For the remaining faces, for all these faces, E bar is perpendicular to A bar. Therefore, flux passing through them will be 0. So, flux passing through this EFGH is equal to flux passing through this ABCD, that is equal to flux passing through this ADEH, that is equal to flux passing through this BCFG. So, for all these places, flux will be 0. And so, now if I ask the net flux passing through the surface, so net flux passing through the surface is, so net flux is equal to, all these are 0, so directly I am adding them. So minus EL square plus EL square, and so that net flux passing through the surface is also 0. I am not making any conclusion here, just the net flux for the given cube in this case will be 0, right? So that is a way of calculating the flux area. So flux to the different phases you can calculate here. That if the field is uniform field, then calculation will be easy for us. If the field is uniform and if the surface or plane surface is like this, then just we need to identify the angle between the area vector and the field. So while writing the angle, should keep in mind that area must be taken as an outward normal for the closed surfaces. So right, so according to that, for this face we are getting the theta as 90 degrees, area will be outward and the field will be like this. And so that is nothing but entering flux 0. And now the flux is leaving from this surface here, and so that you can take it as angle as 0. So that is a positive flux we are getting here. For all remaining 4 phases, the angle between area and field vector are perpendicular to each other, and so that the flux passing through the remaining 4 phases will be 0. And so the net flux is also in this case we are getting that as a 0. So right. So now let us see in case of non-uniform electric field, how to calculate this flux. So let us take the case of a non-uniform electric field. So our procedure will be same. We define the electric flux to the small area, small elemental area. Then just we need to apply the concept here. We write up for the small elemental area and then integration. So for example, this is an infinite line of charge here having this linear bounded x scale lambda. Semi-infinite let us consider. So it is placed along the axis of the circular ring of radius log here. Now we need to calculate the flux passing through that circular ring. We need to calculate. So write it as a problem. A semi-infinite line of charge having linear charge density lambda, a semi-infinite line of charge having linear charge density lambda is placed along the axis of a circular ring is placed along the axis of a circular ring of radius r, starting from its center as shown. Starting from its center as shown. Find total flux passing through the circular ring. Then find total flux passing through the circular ring. So, right. So here we know the electric field produced by this semi-infinite line at its end. So suppose if I consider this point here, the electric field produced by this. So the electric field produced by this line will be like, we know the components of this electric field produced by this semi-infinite line there. So that means here we can write this one component as that means here you can directly write this component parallel to the line of charge here. That means component, if you are taking this perpendicular, that means here if you are considering actually for this semi-infinite for the finite line we mentioned some components there, parallel component and perpendicular components. So parallel component I can write this as 2 pi lambda lambda by 2 pi epsilon naught r into sin alpha minus sin beta electric field due to this finite conductor. If I write here, just I am taking this parallel and perpendicular components here. Suppose say parallel perpendicular component and parallel component will be like this. So now here this is our perpendicular component. Then our parallel component will be like this is 4 epsilon naught lambda by 4 pi epsilon naught r into, you can write this as like cos alpha minus cos beta, you can write it. So like this we mentioned already these derivations. So in case of semi-infinite conductor, one angle will be 0, another angle will be 90 degrees, we need to cancel. So this angle will be 0 here, the other angle will get to 90 degrees here. So from this we can write this as lambda by 4 pi epsilon naught. Means perpendicular component you will get lambda by 4 pi epsilon naught, parallel also you will get lambda by 4 pi epsilon naught. Suppose this alpha is 0 degrees and the beta value is, let us take it as 90 degrees. So then here 1 you will get and here also 1 you will get. So directly I am taking those components here, right? That means this perpendicular component of electric field is lambda by 4 pi epsilon naught r, and the parallel component is also lambda by 4 pi epsilon naught r. Right? And so here is this is our parallel component now, and this is a perpendicular component. Perpendicular to line of charge. So this is our perpendicular to line of charge component, and this is a parallel to this line of charge, right? So that means now let us take this at a distance of r here. I am taking a circular ring element here. This is a circular ring of radius r. So this is our ring element what we are taking here. So now through that ring element we need to write a flux passing through that small ring element here, right? So through that ring element, now we can write this as that means now we can write it through the ring element. The flux will be there only due to this parallel component of electric field, parallel to the line of charge, and due to this perpendicular component, the area vector, because the area vector of this plane, that means our circular ring will be like this and line of charge will be like this. Now the area of this element I can take like this, and so then this component will be parallel to that area, so that flux will be there, and whereas this component will be perpendicular to that area, and so flux will be same. And so therefore I can write this as flux through small element. So the flux through the small element we can write as d phi is equal to, so I can write write this as E into, that means E parallel into dA into cos 0. That means here this dA also I am taking in the same direction here, the area vector. And angle between them, dA cos theta, so that cos 0 I am taking here. Therefore, this d phi is equal to lambda by 4 pi epsilon naught r into, now dA, area of that element we need to write. So this radius is r we are taking here, and this width let us take it as dr. And so I can write this area as 2 pi r into dr, right? That is the area of the ring element. Therefore, it is d phi is equal to, and so that r will be cancelled, so you will get remaining lambda by here 2 epsilon naught into dr will get. Just integrate this. So lambda by 2 epsilon naught into integral of dr from 0 to r. Therefore, it is lambda r by 2 epsilon naught unit. So this is a electric flux to the ring element of radius if a line of charge is placed like this. So in the same case, for example, if the question is like this. If an infinitely long line of charge is placed along this axis of this ring here, such that both sides it tends to infinity, then what is the flux passing through this ring? Both sides it tends to infinity. The same question, just instead of starting from this end, this side also I am pulling this line of charge here, so that both sides it tends to infinity. And so now the electric flux passing through that ring we need to answer. So electric flux passing through that ring in that case will be, that means if it is placed like this, then net flux passing through the ring will be 0, right? So simply you can take that as an infinitely long, infinitely line of charges there. So if you are taking, due to this line of charge, you will get this flux along this direction. What we calculated here, lambda r by 5 epsilon. That means that flux will be along this direction. That means that is traveling from this say from left to right. And now due to this line of charge, that flux will be in opposite direction there. And so then they are equal and opposite. That means one is positive we need to consider, then other will be negative we need to consider. So the net flux will be when we are summing together. That means when we are adding them, then net flux will be 0. So if the line of charge is infinite line of charge is placed like this, then flux will be 0. So that you should remember. Next, let us take one such a problem, another problem. This again I am taking an infinite line of charge. This is a rectangular plane of length L and breadth V, and it is placed at a distance of say r from this, right? So let us take it as some distance d from the center. That means now the line of plane. Suppose if you are taking this board as a one rectangle, now this line of charge is placed here, symmetrical about that. That means at a perpendicular distance of d from this. Now the line of charge is placed like this. Now from this line of charge, then how much flux is passing through that? So that we need to calculate here, right? So write that as a problem. A rectangular plane, in brackets write L into B, the dimensions shown in figure. A rectangular plane is placed parallel to an infinite line of charge at a perpendicular distance d from its center, d from the center of the plane, as shown in figure. Find electric flux passing through the rectangular plane. electric flux passing through the rectangular plane. Right? I think you got that the situation actually. So here our line of charge is there, our plane is like this. So we are finding the flux passing through this. So here also the same thing similar to that of our previous problem. The electric field is non-uniform on this plane here. Its line of charge is here if you are taking the different points here. So here if you take on this plane on the board, if you take in this point here, then you will get one flux. If I am taking a flux at this point, electric field another magnitude of electric field and direction also different here. Because the distance of the plane from this point is different, distance of the line of charge from this point is different, and distance of line of charge from this point is different. So they are different there. So then we need to calculate that both the magnitude is changing as well as direction is also changing here. So now suppose I am taking the situation like here, I am taking one element like this. This is our element what we are taking. Let us say this element is from the symmetrical axis, this element is at a distance of x here from the midpoint. So this width of this element as dx. So now the electric field in that region will be along this direction you will get. This is from the center, I am drawing this line here. Now the electric field at this point will be along this direction you will get. So this is our x, this is our d. Right? And so such a symmetrical element you can cancel that side also. Right? That means this side of the symmetrical here. That means here also you can cancel such a one more symmetrical. So I am just what I am doing is I am calculating flux passing from this one side of this symmetrical line. The same flux will be there on the other side also, right? That means actually what I am saying is if suppose I am taking this as a cross section of this plane, and this is the line of charge I am taking as a point here. This is our D. Now this is our small element what we are taking here at the distance of x from this. And I am saying this side also the flux will be there here. That means here also that element will be there at a distance of x here. This side is totally b here, right? So what I am taking is I am calculating on the one side here. Here the electric field will be along this direction we are getting here. Similarly here electric field will be along this direction. So one side we can calculate or we can double. So that means here now the flux to the small element I can write as d phi is equal to A into dA into, here the area element will be like this, dA. So this angle I am taking as theta, so that this angle will be theta. So here also this angle will get theta, right? So then dA cos theta. So here theta is also variable. In the previous problem only field is variable but theta is constant value. So here eval is variable as well as theta is also variable. So let us substitute those values now. So E value. So E is nothing but electric field at this distance. Let's suppose this distance is R, where R is equal to, I can write this as root of d square plus x square I can write. Right? So then this is lambda by 2 pi epsilon naught R formula. That R value we can write as under root of d square plus x square. Is it clear? So lambda is infinite line of charge. So infinite line of charge means you can write it as lambda by 2 pi epsilon naught R. That R is given by this expression into dA. Area of this element we need to write. So clearly you can write area of this is a strip. You will get rectangular strip. So its width is dx and length is L. So its area I can write as L into dx into cos theta. Now cos theta value you can write from this angle. This angle is theta, or you can observe here. This is the line of charge we are taking here. Perpendicular to this we are taking. That means I am drawing this diagram is about if you are observing from the top. If you are observing from the top, this is our line of charge. This width will be B here. From here to here, the width is B. That means this side. We are observing from the top. Then you will get the situation like that. And so now this cos theta value we can write as d by under root of d square plus x square. Therefore, this d phi is equal to lambda L by 2 pi epsilon naught is a constant value into d is also constant. So that the remaining is dx by d square plus x square unit. So then you get the total flux. And then you can multiply with this 2 here. Because here, as I said, if you are multiplying with 2, or you can take the limits as from 0 to p by 2, you can take. That is your choice, you can consider here. So I am directly multiplying with that 2 here. So multiply with the 2, then limits will be from 0 to p by 2 we need to consider. So total flux will be 2 times the integral of d phi. So why we are writing integral of 2 pi d phi, I think you know. Or here itself we can write here by taking both the elements here. So then this value is from x is varying from 0 to b by 2. So only from here to here, that means from here to here we are integrating and we are multiplying with the 2. This side also same flux will be there, so that's why we are multiplying with this 2 here. And so then this value will be 2 lambda L d by 2 pi epsilon naught into integral of dx by d square plus x square. If integration is completed in mathematics, then you can solve yourself. It's a direct formula only, tan inverse formula you will get. Otherwise, we need to substitute those calculations here. Like by using substitution method, you can do this calculation. Let x is equal to, by using this, x is equal to d tan theta, we can write here. Then dx value is d tan theta means that is secant square theta d theta. So you can substitute that value there. Therefore, it is phi is equal to 2 lambda L d by, the 2 will be cancelled there. So lambda L by pi epsilon naught into integral of the dx value is d secant square theta d theta by, you can write this as so 1 plus, that means d square I can take common here. So d square into 1 plus tan square you will get. 1 plus tan square is nothing but secant square theta. Then simplify the equation. To simplify this, only you can write this as phi is equal to lambda L d by pi epsilon naught. That the d also can cancel here, 1d. So that means here d into d square you will get, the d square will be cancelled. So then only integral of d theta you will get. So then integral of d theta from, let us say, from 0 to theta, 0 to 5, let us consider for example maximum possible value. So then lambda L by pi epsilon naught you can write here, right? Now that pi epsilon naught into 5. That phi value we can write by using this equation here. So directly I am substituting there. So lambda L by pi epsilon naught into that expression we can write that value as tan inverse of x is nothing but b by 2. So b by 2d you will get. Is it right? So finally I am writing that expression here. So that phi is equal to, that flux is equal to, this phi is some flux here, that is maximum angle, or you may consider this as some, because phi we are using for the flux. Let us take that angle as some alpha. So that means lambda L by pi epsilon naught into tan inverse b by 2d. I think all of you got this, how we are replacing this alpha. That means just by using this, that alpha is nothing but I am taking up to here. That means that alpha means I am taking this as maximum possible angle here. This side is suppose say b by 2 and this angle I am taking as alpha. So then tan alpha you can write here, b by 2 by b, d this is. So then b by 2b you will get, there is nothing but what we are substituting. That means when you are here, the angle will be 0. So that 0, and when you are here, the angle will be alpha. So that here I am taking the limits as from 0 to alpha. And finally you will get alpha, and tan alpha you can substitute like that. And otherwise, for example, example, if you are not multiplying with this 2 here, for example, then here we need to take the limits as from minus alpha to plus alpha we need to consider. That means this side minus alpha, this side plus alpha. So minus alpha to plus alpha we may consider. That is our choice. We are multiplying here with the 2. So directly we can calculate like this. So it is some flux calculations here. So that means whether the flux is, whether the field is uniform or non-uniform, we can calculate the flux calculations like this. So whenever a charge is given, that means whenever electric field is known to us, and we can calculate the flux passing through the given area. So if the field is variable, either in magnitude or in direction, then we need to, or both like this. Here you can observe that in this problem, electric field is varying both in magnitude as well as the direction. So we write the small element, the flux passing through the small element, and we integrate that, so that we will get the flux passing through the entire given surface there. So such a problems will be there in that material or in the Singh's book. So you can solve those problems. And in the next class, I will start about this Gauss law. This is just flux calculations only. And in the next class, I will start about this Gauss law and importance of the Gauss law, and some important derivations will be there from this Gauss law there. So I will explain that in the next class. Thank you.